So we're continuing looking at motion maps, and we got this ticker timer that's like a model of a ticker timer. Dots have been laid down 0.1 second intervals apart. We've already come through and we've made ruler measurements of how far away each position is away from the origin, and we've recorded it in an observation table. So I've already sort of filled this in. I'm going to pull this in and do the reveal kind of method rather than like writing it out loud, because I assume at this point you guys have done the thing, right? So we make our observations, and these were my observations from this ticker tape. I just recorded this data, which we're modeling this, but like in a lab, you would have used a ruler to make the length measurements, like a meter stick. You would have used the dots themselves to tell the time, okay? And so we've got this data table. Notice it doesn't fill the whole data table. That's fine. It shouldn't fill the whole data table. If you put 0, 0 as one of the data points, that wasn't necessary, okay? So that's the only reason there's that extra line in there is to remind me to draw attention to that. In terms of the significant figures, what we're going to assume, and here in my writing, I assumed that there was 2 significant figures with the time. I'm going to draw your attention to this as well. We're going to assume that there are 3 significant figures for our ticker timers. 60.0 hertz will be their recording frequency. And so we're going to continue to assume that our time is 3 significant figures. And that's something that's not clear on this page. If you're somebody who's trying to sort through that significant figures with the equipment, by all means talk with me about it, okay? We'll talk about the precision of our equipment. Now, I take this data and I graph it on a position time graph. And here we got a position time graph. The scaling that I used was every 4 squares was 0.1 seconds. I know there are going to be people in the room that use a scaling for the time axis where every 5 squares is 0.1 seconds. I would be cool with each. In fact, if you used every 5 squares 0.1 seconds, people that did, show of hands, it fit on the graph, right? Just barely. So that would be a fine scaling for this axis. We've got time in seconds, we've got position in centimeters, and really we should be underlining these things and getting into those good habits. We should have a title that's descriptive, position in centimeters versus time in seconds for a motion map. And in this case, because we don't have any further context, like we don't know if it's a car or whatever it is, we're just going to call it a motion map, okay? But if we knew more, we'd say more. Now, once you've got all this plotted, we've got a rate triangle. And what you are allowed to draw on a graph is a rate triangle, or a tangent, or that kind of an analysis if we're doing hand-based analysis. If we're not doing computer-based analysis, you could draw those things on because it's a part of your work shown. What you're not allowed to draw in the graphed grid space is calculations. And so underneath of a graph or beside a graph, you could have your rough calculations, or you could place your calculations at the end of your lab report, and you could call it, for example, Appendix A, slope calculations for figure 1. And that could be an attached page at the end of your report, and you would say underneath your graph, for slope calculations, see Appendix A. That would be a reasonable thing to do, and we would attach this as its own separate page, just stapled to the back of the report with an appropriate descriptive title. And the appropriate descriptive title, although I don't have enough space for it right now, would be Appendix A, slope calculations for figure 1. That would be a nice appendix title for this thing, okay? Now, once we've done that slope, I get it to be about 96 centimeters per second. And as I was walking around the room, some people in the room were saying it was around 100. Now, I'm choosing 2 points, not actual data from the original observation table, but 2 points that landed on what I observed to be good vertices based on my time scaling. That's why I chose these 2 points, was based on my time scaling and the fact that that line of best fit went through those vertices. So they're data points that lie on the line. They're not necessarily observation points from my observation table. Is that clear to everybody? Yeah? Give me the nods of the head if it makes sense. All right. So then I take this value and I plot it on a velocity time graph. And yeah, we can have a descriptive title, but in terms of the scaling, well, since I only have a constant velocity, really I'm just kind of trying to fill this vertical space with data. So your scaling may be different than mine. I went 40, 80, 20. Yours might be different. The main point here is, though, that since the slope is the same the whole duration of the first graph, the velocity is the same for the whole duration of the second graph. And I did see one group where they had a data point here, and from here forward it was horizontal. It was a constant velocity, but they had a velocity that went from the origin up to there. But we don't need to do that. there was no data that kind of like jumped from 0 meters per second up to here. The velocity was the same the whole time. So the velocity should be the same the whole time, okay? So just to make sure that we kind of have that idea that it's okay for it to be a horizontal line, it's okay to be constant, we don't need to make those kinds of jumps, okay? Constant slope is constant velocity.